The plan today is to have another, go through another sort of sample question here. Projectiles part 2, or how I threw that guy out at second base. Maybe done that three or four times in my short baseball career. Well, I don't know. I had a pretty good arm, but they didn't steal on me because I knew I had a pretty good arm. Yeah, one of those, you know. So we're going to be looking at a sample question where it's a projected but on level ground, that kind of thing. Okay? So you can write them down, you can sit back, you can enjoy. There are clicker questions that as we go to sort of keep you focused a little bit. Whatever you think you need to do that will learn you the best. Okay? Projectiles part 2.
Doesn't it teach you the best?
Yeah, I was just being silly. The first one you'll remember we were doing a drive off a cliff kind of thing. The second one we're going to do is a projection on a level ground, and then probably tomorrow I'll do the Big Daddy part 3, which is projection off a cliff at an angle. Okay, so, this is good. Let's just press play and see what happens. Now, what do you notice about the dots? Hark. I'm broadcasting to the world here. What do you notice about the dots? The horizontal distance between them should be the same, and you can't really see it, but no, I guess you can. How much below is that one from that one? Hardly at all, right? But here, that one is clearly much below that one. So the vertical distance between them is increasing quite a bit, right? Now, I think I can actually take my gun down here. Can I do this? Can't?
Yes, it can. Jeez.
Yeah, so what I'm talking about is, no, not that. There we go. Yeah. I could just do this all day.
Make it fire straight up and down.
You want it straightened down?
Or almost. Keep going.
I'm trying.
Jeez.
So that's kind of fun too. Okay, so consider a projectile like a bullet launched at some angle. So true or false with the clicker. True or false, the vertical acceleration remains the same throughout. The vertical acceleration remains the same throughout. Correct answer is true. Vertical acceleration. What is the vertical acceleration? Minus 9.8. It's gravity. Vertical acceleration remains the same. Okay, chance to redeem yourself. Oh, didn't mean to do that. The horizontal the horizontal velocity remains the same throughout. True or false? Correct answer? Yeah, it's true. Horizontal velocity remains the same. There's no force acting on it horizontally, except air resistance, right, Darren? Horizontal velocity remains the same. There's no force acting on it. Okay, so here's a sample. I think this is this one? Yes, it is. Okay. So a ball is hit at an angle of 30 degrees and leaves the bat with a velocity of 40 meters per second. We'll call that the muzzle speed, right? It's the initial velocity. Whatever it is called, it's the speed right there, kind of thing, right? So tell me, what is the vertical component? Tell me what is the vertical component? You'll need it. So to find the vertical component, remember what we're talking about there is, this is the vertical component, that's the horizontal. Vertical is opposite, so we're talking about the sine, and so it's just VV is equal to V sine theta, 40 sine 30 is all it is. 20 meters per second.
Yeah, buddy.
Good? Yeah, that's okay, Carolina? Yeah? You probably knew how to do it, you just didn't realize you knew. Yeah, I know. Guess what's coming up next? What do you think? Could it possibly be the horizontal? Let's just see here. Don't look. Yeah, it's horizontal. Oh, and then I still messed it up. Horizontal. Tell me what the horizontal speed is. Maybe you've got it already figured out. Oh, Parker was 34.6. Yeah, it says V cos theta, 40 cos 30, 34.6. Okay? When you're doing any projectile question, you're going to need both those numbers. So, like, without any question, start by finding those two. Okay? Guaranteed. 2 marks, right? You got to do them. Okay. Now, time of rise. To find out time of rise, we're going to use VF equals VI plus AT, but the question is now, because I've got 2 velocities, which one do I use for my VI? Do I use my 40? Actually, I've got 3, don't I? Do I use my 40? Do I use my 34.6? Do I use my 20? Or do I use minus 9.8? Which one do I use for VI when I'm solving for the time of rise? What do you think? Which one are we going to use for time of rise? How do we do? Because it's time of rise, we have to use vertical component. Because it's time of rise, we have to use the vertical component. Okay? So we're going to use VF equals VI plus AT. Now, does it matter whether it's positive or negative? Absolutely. Okay? Absolutely matters here. The vertical initial component is plus 20. It's up. The acceleration is minus 9.8. That's imperative. You have a negative there, and you get a time of 2.04 seconds. So it takes 2.04 seconds to go up. Okay? Good? All right. So what about height of rise? Oh, there's no questions here. All right. So how am I going to find the height of rise? A couple different ways we can do it. How the vertical displacement. So if I'm doing vertical displacement, I have to use what kind of velocity? Vertical velocity, and I have to use vertical acceleration, which is minus 9.8. And Darren needs to put his phone away. So I can either go VF squared equals VI squared plus 2AD. You'll notice that I've got a 0 in here for my final velocity. How come? Because the final velocity at the peak, at the top there is 0, right? That's how we know it's at its maximum height. So that's 0. The initial is 20 plus 2 times minus 9.8 times d, and you get 20.4. And you should get a positive 20.4 because that displacement is up positive 20.4, right? This is 20.4. That's one way to do it. The other way to do it would be to say d equals VIT plus a half AT squared, because you know your time of rise. Again, I have to use a positive 20 here. Time is 2.04 plus 1/2. You have to use minus 9.8. 2.04 squared, you should get exactly the same. I don't know, which one do you think is easier? Probably the first one. Certainly your choice. How about the time of fall? The time to drop 24 meters. If it went up 20.4, then it has to come down 20.4, right? So time of fall. The only difference is now I'm falling 20.4, and so that 20.4 should be what? Negative. And what do you know? You put in minus 20.4. VI, the initial vertical velocity here is 0 because it's falling from rest, from that peak, plus 1/2 AT squared, that's minus 9.8 T squared. You get a time of 2.04 seconds. Shouldn't be too surprising that it's exactly the same time, right? The time up should equal the time down. Again, this is neglecting air resistance. What about the time of flight? Now, the time of flight, there's a whole bunch of different ways we can do it. The actual time of flight, like really, the actual time of flight, the displacement for the entire trip is 0 because I start at ground level and I end up at ground level. So the displacement is equal to 0. Okay, so one way to do that, oh, I gotta make some room here. One way to do that, oh, that's no good. That's better. One way to do that is to say that the displacement is 0. My VI is 20, positive 20, t plus 1/2 minus 9.8 t squared. The only problem with this one is you get 4.9 t squared minus 20t equals 0. What kind of equation is that? Starts with a Q and people hate them. Quadratic. Do I need the quadratic formula though, Troy, to solve that? Why not? Come on, think about math. How come I don't need a quadratic formula to solve that 4.9 t squared minus 20t equals 0? It's a binomial. It doesn't have a c value, right? Okay, and so in fact, what can I do here? I can factor out a t because, and that's going to give me t is equal to 0. Of course the displacement is 0 and time is equal to 0. It's just sitting there, right? At t is equal to 0, it's on the ground. It hasn't moved. The other t is going to be when it goes up and then goes down, okay? So, looks like I've got the first one here is using the quadratic formula, right? And I get 4.08. Big surprise there. 2.04 up, 2.04 down. Okay? You could also just say T up is equal to T down, right? Of course, you can do that. A whole lot easier. Now, there's a reason I did it this way, though, Calvin. I wanted to show you that. Okay? If you've got something projected off a cliff like this, even though it goes up, like let's say your cliff is 100 meters tall, you can say your displacement is minus 100, and it's going to take into account the up and the down, and it's going to do it for you. That's when you are going to have to use a quadratic, but I just wanted to show you that that works for level 1 as well. Okay? Obviously, I would encourage you just to do this way. The other way you can solve that is to simply go t times 4.9t minus 20 is equal to 0, t equals 0, or t is equal to 20 over 4.9, and what's that going to be equal to? 4.08. I mean, you can just factor out a t and that'll work too, right? Yeah? What about the range? The range is how far does this object go horizontally, right? Now here's the tricky one. When I'm dealing with range, because it's horizontal, what velocity do I have to use? I have to use the horizontal component. You can't use vertical. What acceleration is there horizontally? What's my AH, horizontal acceleration? 0. Don't let me catch you putting minus 9.8 in when you're trying to find out something horizontally. People do it all the time. Don't do it. Okay? Minus 9.8 is only for up and down. No 7. Okay, so how do I find the range? Because it's a constant speed, it's just v equals d over t. My v is 34.6. My displacement is what I'm solving for. My 4.08 is my time. I get a range of 141 meters. 7. Obviously, that's not me throwing second base. Okay, pretty straightforward. The velocity at impact. I have a question for you before I begin. Will the final velocity be different from the original launch velocity? Remember, the original launch velocity, I think, was 40. Am I right? So as it goes up and then comes down, what will the speed be here at the end? Will the final velocity be different from the original launch velocity? Will the final velocity be different? What do we got for an answer? No. The correct answer is no. The final velocity will not be any different. It will be exactly the same. And let me prove it to you. V is the vector sum of VH and VV, right? The velocity to impact is the vector sum of the horizontal and the VV, right? The VH is going to be 34.6 because it remains constant. The VV is going to be the final velocity for a falling object for 4.08 seconds. Hold on here. 4.08 seconds is the entire time, right? Watch what happens. If I put in VF equals VI plus AT, my initial vertical component is 20, plus or minus 9.8 times 4.08. What do I get? Minus 19.98. It really is minus what? 20. How come it's not exactly minus 20? Like the 9.8 is correct. How come? Any ideas? Come on. The 4.8 is just rounded a little bit, okay? So the final vertical component is minus 20, the same as the initial was. And so you've got a triangle like this, right? You've got a triangle like this with 34.6 there and minus 20. And so how are we going to find the velocity impact? We're going to have to add them together using Pythagoras. So 34.6 squared plus 19.98 squared gives me 39.96, which for all intents and purposes is 40. What's the angle going to be? 19.98 over 34.6, what's it going to be? What was the original angle? Anybody remember? 30. It was launched at 30 above the horizontal. It's going to hit the ground at 30 degrees below horizontal. Everything about this is perfectly symmetrical. Everything about it is perfectly symmetrical, left and right. Okay? Now again, this is only true if what? There's no air resistance. So the final velocity is exactly the same as the initial velocity, 40 meters per second, and the angle is exactly the same as well, 30 degrees. One is just above and one is below. Darren, I thought I told you to put that away. Terrible at that. That is all, my friends. I hope you learned something.
Photon.